Okay, so let me introduce myself. I am Prahlad, and I will just go through some previous topics so that we can and cope up with the assignment that we need to solve this week. Is there any doubt for of the previous test session, or any doubt for the week 4? We can do it. We can solve it, and you can ask me. Otherwise, I can go to the solution assignment solution session. Yes. Yes. Yeah. Course. Yeah. You okay? You can to, you can look at this book, Levine's Molecular Spectroscopy and Macaulay. Okay. Okay. And you can go through the lecture. Okay, the lecture is nicely represented how the this thing is coming up one by one, and it is better to go through the lecture only to better understanding purpose. Anyway, we will look few of them in today's class, and we will go it slow by slow. And let's see. This course has little bit much deeper sense of quantum mechanics in molecular spectroscopy aspect. Anyway, let's start today's session. Okay. Is my slider visible? I hope it's visible. Ah. So, see, the main thing is that for this lecture is how a molecule get excites. Okay. So for that, for I and this two level system, or you can say n level system, the transition probability on going from I to F, what said it's derived like that only. Okay, so the main thing is for molecular spectroscopy, what does it mean by H bar, the perturbative Hamiltonian? So what does the perturbative Hamiltonian do? Is just add up with the without perturbative Hamiltonian part and excite the molecule from 1 to I to F. For in this case, it is the perturbative Hamiltonian induced transition from I to F. So whether it will excite the molecule I to F, that is a question, and that is the thing that we need to that is addressed in the lecture week 3 lecture. Okay, so but the thing is that what is the light? Light is nothing but a electromagnetic wave. So it has a two type of field. One is electric field, one is magnetic field. Now see, these two are field, but we have to incorporate field as a energy term that can be added as considered as a perturbative Hamiltonian. Okay, this electromagnetic wave, some transformation of electric part and magnetic part of the wave or light will contribute to the perturbative Hamiltonian as a potential. Okay, so if light goes like this and your electric field is going like that one, then your magnetic field will be perpendicular to it. It is something like this. Okay, so this is your magnetic field and this is your electric field, and light will propagate in this direction. Okay, so both are three are perpendicular to each other, mutually perpendicular to each other. Now this is a field, so magnetic, this magnetic, there is a magnetic field and there is a electric field. Then we have to incorporate it in a terms of potential so that we can incorporate is a perturbative potential. So in three dimension we can write E as a three component, Ex, Ey, Ez, and similarly B as a function of Bx, By and Bz. So total 6 variable. So last day I say that these are the field. So if you need to incorporate in a potential manner, so what they take scalar potential and vector potential. So if we take vector quantity, then this should have Ax, Ay and Az, three component, and there is phi also. So total it will be 4. Now on going to 6 to 4 there is infinite possibility. So therefore there something need fixation. In electrodynamics it's called gauge fixation. So what these things tell, if you with this we can write electric field as a gradient of scalar potential and time derivative of vector potential, where magnetic field is a del cross A. Now to digress it, to Coulomb added one thing, and that is known as Coulomb gauge fixation. What you get, phi vector potential is 0, and if you see gradient of A, that is also 0. So now this is become minus del A dt and this del cross A. Okay, now these are the two transformation of electric field and magnetic field to the scalar and vector part. Now with this, what is the expression of A? Now this is a hello. Yes. To do that. See, there is a infinite means there is a very large number. You can go for this 6 variable Ex can you can take Ex and By, Bz and Ui like that. So there is numerous way to get from 6 to 4 variable. Okay, but to get a essence of scalar and vector potential, the electrodynamics, they use this kind of fixation using scalar potential as a phi and vector potential as a, and they have some their expression which is shown it like that. Okay, so easily you can go from here to here. Okay, so anything else? So now see, now the question is what is A? So A is a plane wave. This potential, the representation of A can be written as A0. This is a unit vector along the electric field. Okay, and if we write plane wave, then we have to write this. Okay, now look at one thing, then the direction of vector potential A will be along the direction of electric field. Now if it represented as a plane wave, then what will be the expression of E? So as I mentioned earlier, E is nothing but dA dt. So if I take a time derivative, it will look like now if I take I omega common, then it look like okay. Now see this function and this function, their direction is same. Now if you think kr minus k dot r minus omega as theta, yes, so E is equal to h cut by E is equal to h cut omega. Okay, so if you think kr minus omega t as a theta, then your A ka expression with some constant you can think as a E I theta plus E minus I theta. So this equation is proportional to the cos function. So this is a cos function. Okay, cos of kr minus omega t. Similarly, is E I theta minus e to the power minus I theta, it will be the sine function. So however, electric field and scalar potential have the same direction. E, A and E are out of phase by 90 degree. Okay, so this is the first part that we need to understand. how we convert to plane electric field, the relationship between electric field and plane wave. Okay, so with this, the first question we can solve for today. The question number 1 is, electromagnetic field. Okay, so the first option is the wave oscillating with time with an angular frequency omega, okay, in the direction of wave vector k. So that is correct. Second option is that wave function has an amplitude of a0, okay, which has a direction around the unit vector a. So these two are correct. Third, both the vector potential and electric field oscillates as sine omega t. So if you look at the this thing, this is e I theta minus e to the power minus I theta. So this is corresponding to the sine omega t somehow. Okay, but as I mentioned previously, if this thing plane wave vector is in sine function, so in the previous deduction we see the if plane wave is a function of cos function, then your electric field will be in sine function. So both here you can see the sign has been changed. So it is sine. If it the scale vector potential is a sine function, then your electric field should be out of phase. That should be cos function. So this is a incorrect option. Now the vector potential oscillates as cos omega t, whereas electric field oscillates as sine omega t. So you can see this. Just look at your assignment. Is it minus or plus? If it plus, then it will the option is correct. And if it in this if this plane wave function expression of plane wave function has negative in between, then it will the option is not correct. Okay, it will be reverse. Okay, so for that expression of plane wave function, this option is incorrect. It will be only correct when this the wave function the expression of wave function has a where the two plane waves are in are positively added. Okay, now so the thing is that now we know how to incorporate it. Now one thing is that when a particle, now the particle is exposed to the electromagnetic field. So now when the electromagnetic field is exposed to the light, particle is exposed to the light, the particle will show a another force to the electromagnetic field opposing to it, that is denoted by Lorentzian force, which has a expression that this is velocity of the particle. E and B we know, and Q is the charge. Okay, now for electromagnetic field, we just we can ignore the magnetic part. So we can write your Lorentzian force as a Q into E, ignoring B, contribution from B. Okay, now so at light off condition, then no perturbation, so H0 will be, you know, P square by 2m plus Vx. Now if we switch on the light, then this Hamiltonian is no longer H0, it has some term. So your this thing will change. So your momentum, sorry, this is P0, you can take as a P, is nothing but, sorry, P0 P0 speed dash. Okay, now the thing is that we know E is equal to dA dt. So your FL will be minus Q into dA dt, or we can write is dt of Q dot A. On the other hand, force is a force, you can make it as a so this thing so MA can be written as PT, or so ddt of P. So if we equate both of them, what we will get? P dash is equal to minus QA. So we incorporate this thing when light is on. Okay. Now the second question, just we will extend it to next thing. Just keep it there for it. Okay. So the second question, what it says. Okay, we need to go a little bit further for that. So now in H we can incorporate P is a P0 now we just so as a function, so we have to write it like that. Sorry, P0 2m QA minus QA 2m P0 Q square A square by 2m plus Bx. So if we take these two term, this is nothing but your H0. Okay, so we can write this whole term say H0 minus P0 by 2m QA 2m P0 plus Q square A square by 2m. So this is total is your HT, H what T, H comma T, perturbative Hamiltonian. Now in case of weak perturbation, we can just this value will be made, we can just remove this thing. Ignore. So we just left out by so expression of P0 is nothing but minus IH cut T by dx of A d by dx. Now if we take this thing little bit more carefully, then what we will found, so so it can be write as del dot A psi x and A into del psi x. Now from Coulomb gauge we know this is 0, so we will left to it by so IH that will be A del and this is also A del. So total IHQ by M A del. So this is the expression of your perturbative Hamiltonian. Now we know the if we take a minus I, so Q by M A minus IH cut then, so what we will get, this value will be Q by M A dot P. So your perturbative Hamiltonian nothing but is a multiplication of vector potential A and the momenta of the particle. So now using this, let's solve this, using this concept let's solve the second question. 2 for a particle with charge Q, mass M and momenta in an electro field of dot potential A, the relation T is Q by M A dot P is correct under the condition A force experienced by the particle F equal to M into E as external So let's go by point. Okay, so force experienced by the particle is m into e. So as I mentioned previous, the force experienced by the particle is q into e, not m into a, m into v, m into acceleration, but not m into e. So e is a electric field, so this should be a q. However, the other thing is correct. External magnetic field is 0 by electric dipole moment approximation. So this is incorrect option. Now, as I mentioned, the electric field is written as a dA dt, and under Coulomb gauge Coulomb gauge we take psi is equal to 0. So this is a correct option. Now the momenta p of charged particle remains unchanged in electric field is not correct. So you can see the momenta is changing depending on the electric field, that is the electric field between light, amount of light exposed to the particle. So this is also an incorrect statement. Now the contribution of a square terms to the total Hamiltonian can be ignored as a weak perturbation limit. That I showed it here as at a weak perturbation limit we can ignore this term. So that is a correct option. So second question is done. Now let's move to the third one. So third one, that doesn't need any derivation. And now the wave vector k depends the dependence of the interaction potential in the Hamiltonian for a molecule can be ignored Now the question is that what is the interaction of molecule with a light? So this, if I think this is a, and then this difference you can say as a wavelength. Okay, now if I think the molecule is extremely smaller than the molecular dimension is extremely smaller than the wavelength, so you can think the molecule is sitting over here. So for it, the wavelength is infinitesimally high. Therefore, it could not sense what is the change of electromagnetic field. Okay, so for interaction, molecular dimension should be less than the should be much lesser than the wavelength. So first option is incorrect. Now the question is that what is the wave vector? So wave vector is the expression is k 2 pi by lambda. Okay. So this option is incorrect. The frequency of the field is much larger than the molecular dimension. That is not also correct. Wait. What is saying? The frequency of the field. Now what is say the lambda is infinity. As I mentioned, the lambda, if it lambda is infinity, yes. No. See, for if a molecule, the molecule should be infinitesimally smaller than the. See, this molecule is so big, so it can sense the change of electromagnetic wave. But if the molecule is so less, then within, if it sit over here, then it will not see any change of electric field or magnetic field. It's constant over there. You can stay. It's just a point. Okay. Yeah, that is the thing. I also thinking. So this is not a correct option. So let's go by this thing. Just yeah, yes. This option is not correct. Sorry, this is the correct option. What is written on your manual? Is this solution is up or not? Only D is correct, no? So one thing, this I guess this is correct option. I just need to talk to it in rest, and then I will in next lecture I will tell what will be the correct answer. Okay, so this is something disputed. I think logically this is a correct answer. Okay, so okay, and the last option is also correct. Lambda is infinity, then k should be 0, 2 pi by lambda. This is the option. Okay, so I will discuss it. I think it is a correct option. Okay, now question number 4. So correct statement about a dipole, electric dipole Hamiltonian. So number 4. The first option for a electric dipole Hamiltonian for a particle of charge q given below is this. So why we derived it? Because we have to evaluate this h comma t, is it capable for a particle in I state to excite to the f state. So the integral f h comma t I governs the selection rule. That is a correct. Now according to electric dipole approximation, the spatial variation of electric field amplitude over the region space occupied by the particle cannot be neglected, but it can neglect it because I saw show it previously. The size of the molecule is so less with respect to the electric or magnetic electric field or electromagnetic radiation, so you can neglect it. So this is a incorrect thing, and this is neglected, otherwise this equation will not come. Next, E0 is the maxima of the amplitude. You can see that if you the E I omega t plus E minus I omega t, that will give you the cos function. The maxima, the cos function is oscillated in between -1 to +1, so maxima will happen when it is 1. So the maximum value will be E0, and while and the thing is that its direct what E cap represent as a unit vector. That is okay. For a vector quantity there is a unit vector is there. Okay, so now so electric field is a the electric field is a function. You can say E0 cos omega t something is oscillating electric field. We can write it as a E0 cos omega t, as cos function is oscillating function and it can be in between -1 to +1. So the maxima will be the E0, and the field vector is aligned as a with at E direction with unit vector E hat. Now, so with this equation is given, we have to check it is applicable for n number of particle or not. So what is given? H comma t as a E0 omega cos omega t 0 omega 2 m omega e I omega t e minus I omega t. Now it can be written as 2 cos omega. So total will be E0 m omega cos omega t now for n particle system it can be written as E0 by omega. We can take out cos omega t. Now charge, I missed the charge over there. This is Qn by Mn where n is the moment of the n particle or nth particle, or qn and mn is the charge and mass of the n particle. So this is the correct option. Okay. Moving to question number 5. If Hamiltonian H0 is given by h cut 2m delta r square, the value of okay. So let's do it. Just a minute. So what I have to mention H0. So let's this up, take a operator fr. F is a function of r, and let's see what will be the result. That's what we know. Okay, so we put the value h cut square m minus plus 2m r square fr. Okay, now is the expression of delta r square r fr. So we can write as delta r so it will become 1 into fr or r delta r of fr. Secondly, so what will get fr 1 into delta square fr and 1 into delta r fr plus r into delta square r fr. So this is the expression. So you can write h cut square r m delta r square fr plus 2m delta r fr So these are 2 into 2 plus h cut per square by 2m r delta r square fr. So these two cancel out, so what we get is 2m sorry, only m delta r fr. Now if I multiply it with minus hr, then it will be plus. So this is nothing but IHP to m fr. So commutation between R and Hamiltonian will give you result IH cut P by M. So this option is the correct option. Okay, so now let's do this question number 6. Conditions for a transition to take place with absorption of light by a molecule these are so suppose is a propagation of a light and electric field is something like this. With a unit vector plus E minus E. Now a molecule AB so having a permanent dipole moment which is around, you can think like that or other way. Okay, so now the question is that now is the suppose this molecule is aligned like here. The dipole of this molecule is aligned like this, mu of AB. Therefore in that case, case 1, mu is perpendicular to AB, then dot product is nothing but cos 90 degree, so that is will be 0. So there will be no effect, no effect, therefore there will be no transition. Now if we think the molecule is aligned like this, some mu AB. Now in that case mu AB is parallel mu AB is parallel to electric field. So if you take mu AB dot E, or sorry, or E, anyway vector thing is A dot B or B dot A same, so that value will not be 0. So in that case transition will occur. So this case and this case, A and D, are the correct option. Now there is another third case. If the molecule is aligned like that, where mu AB have a projection on this. So in that case also transition possible. So this is a third probability where also transition can possible. It should be either parallel or there is some projection of dipole moment on the electric field, so that the the scalar product between dipole moment and the electric field should not be 0. If this two is 0, then there will be no transition. And why there is no transition? Because we know if we look at the Hamiltonian, some constant, it is so comma t, you digress it so much, then it will get mu dot E or E dot mu into I. So if this value goes 0, there should be no no excitation or transition. Okay. Now question number 7. The correct expression let's do one by one. Okay. So if I look at the expression of transition from I state to F state, this is all we know. Now if look at this, and if we incorporate the expression of H cart, which is nothing but then after solving all this thing, what we will get is equal to where E is equal to electric field E0 into this, so it can be now put this value here. So what we get as there is a mod, then I square is equal to -1. As a mod we can take as a positive one, and then we have to write cos omega t. Okay, and here one term will be also coming out. If E dot mu I square, so E0 H cart square omega I F by omega square omega t square. So I think this is the expression of the first option. Yeah, so this is a correct one. Now let's do little bit more. So this thing, okay, omega if is the difference between these two states, okay, and omega is the angular frequency. So if is I to f. If you can write it I omega t minus I omega t by 2 f square. So it will be come out E0 4 h cut square if comma t I omega minus omega if t plus e t into this is the second expression. Now this expression has a minus, so it is a incorrect. And this is correct, so only there is a fourth term is missing, otherwise the expression is correct. That's just a addition of multiplication of a constant. Okay, so next this is there. Now okay, one thing I missed here. Okay, let's do little bit more. Okay, so t to t dash. Now we are telling that light is in between 0 to time light. So if we look at the pulse, so this is 0, this is a t1. So if I take minus infinity to plus infinity, nothing is changed, we are just adding zeros. So we can write 0 to t2 is minus infinity to plus infinity. However, the light is only work on between 0 to t dash. Okay, so this expression can be written as zero So this is transformation. Okay, so now this equation is correct on that space. Now so here in one mathematical expression is added, which is not Fourier transform. Is a Fourier transform of an integral. So if we take xa and do a Fourier transform of the integral, it should like so. If we multiply both of them with 2 pi, plus infinity 2 pi dt plus 2 pi omega f minus omega t dt square. So 2 pi we have to multiply with 4 pi square. So it can be written as delta of omega if minus omega t, and this can be written as delta of omega, sorry, this is positive, if plus omega t. Okay, so hold the expression should be p0 pi square by h cut square omega if by omega square delta plus so this is the another expression. Okay, with this we think this correct option is also correct. Is there is some constant may be there, otherwise this equation is correct, and there is a delta which is a printing mistake, that you know that is just a printing mistake. Okay, so now what these two means. So omega and omega, if so this thing these are called Kronecker delta. So if WF so this value is either 0 or 1, so also either 0 or 1. Okay, so if it's 0 then WIF equal to W, and this is or okay, or we can write W is equal to so this is negative sign, so this is corresponding to simulated emission and this is corresponding to absorption or stimulated absorption. Without simulation, absorption will not happen. So there is nowhere it's mentioned it's simulated emission absorption. It's already known absorption is simulated absorption. So this part is absorption, this part of emission. Okay, So this is the two different process, and one thing is that, sorry, simulated emission. Okay, one thing is that the absorption and simulated emission cannot occur simultaneously. When a particle getting excited, it will only excite, and on that time when it in excited state, it will emission, it will show emission. So this is excitation and this is the excitation, and they both cannot happen, not take place simultaneously. Okay, now so I have picked the option. So now question number 8. Hello. D. Yes. No. Four is not needed. You can, if you start the lecture video for week 4, I think you send that there is a correction on there. Okay, it's just a modulating factor. Question number 8. The correct condition under which the stimulated emission will take place. These are R. Delta Okay, as I mentioned previously, this is a chronicle delta. As So in the beginning of first two lecture, I showed an example of particle in a box problem, where we can say the wave function are orthogonal to each other, where we represent the orthogonality as a Kronecker delta, where we see if the the wave function are normal to each other, and two different wave function are orthogonal to each other. Okay, so with this analogy, so delta here in this case of particle in a box, so orthogonal means the Kronecker delta value will be 0 when the two wave function are not same, and it will be 1 then when the expression of two wave function are same. Okay, so with this analogy we just look at the we just look at the options and pick out which are correct. Okay, so for first question, the delta of W if Fi minus W is equal to 0. That is only possible when Fi is not equal to omega, and these are all deltas. Again a printing mistake. And okay, when so first one option eventually is incorrect. Now the second option, Fi plus omega is equal to 0 for Fi minus omega. Okay, so this is also incorrect. So if Fi when and not equal to 1 when sorry 1, so this option is also incorrect. Last third option is minus 1 when Fi minus W is 1. Okay, and F minus not equal to W. Okay, so it's not is equal to 1 when W is equal to 1, and W minus W is 0 when Fi not equal to 0. So this option is correct. And eventually this option is also correct. Okay, with this the last two is left over. Question number 9. So correct expressions for probability of absorption from initial state to final state, or R A T square B Okay. So 4 options are given for the absorption probability from I to H state. So okay, let's take some more slide. Wait a minute. Okay, so this is the expression. So for simulation so absorption case, the expression should be EFT pi square E0 square W Fi Okay, WIF is minus of WIFI. If you take the square, both are same. Del So with this we can say the second option is correct. Okay. Okay, sorry. End option. Now if I so expression of this is 1 by 2 pi ei minus infinity to plus infinity square. Okay, so it should be so if we ignore the constants, so we can think we can see that this expression is matching over with the option number D. So for 9, A and D are the correct options. So let's the last question of this session. So then the correct statement to variables is or are conjugate variables are not true based on our lecture, we can tell that the fourth option is correct one. Now I just tell you one thing about Fourier transform. Suppose any spectroscopy like IR spectroscopy. So in case of Fourier transform IR spectroscopy, what happened? The spectroscopy, the spectra is converted from time domain to frequency domain. Okay, so time and frequency are conjugate to each other. So if we multiply these two, time and frequency, we will get a dimensionless quantity. So option C is correct. Okay, in that sense we can say that. Now let's take another example of two conjugate variables. You can take this x and px, where x is displacement and px are momentum. Then they are related to the Heisenberg uncertainty principle. So this option is incorrect. On the other hand, if we multiply the uncertainty of delta x in delta px, they will give a finite value and they will commute. Okay, sorry, they will not commute. Sorry. So if you take these things, they will not commute. Okay, so this is also incorrect. Okay, for the last question, the option C and D are correct option. Okay, with this we can stop it here, the assignment session. Any question you can ask if you have, or I will just give a overview of the upcoming lecture. So yeah, this is for this week. Okay, my is off. Okay, so this is for this week, and the next week the theme of the lecture will be, now what will happen when you the light is exposed. So just for now we are just looking at the transition probability PFT, which is given by a expression like this. Now this function, if you can convert it to the this is a delta function. You can see that this is a delta function which can be written as a sine function, and you can see this, there is three part of the function of in case of absorption, where this first part will give you the intensity, intensity, and this delta function will give you the FWHM or line width of the absorption spectra, and this thing is already known, this will give you selection rule. And the second thing that we will show in the next lecture, till now we are considering its discrete absorption from I to F. Now what will happen when F is embedded with so many excited state? Now you know that if we for a simple hydrogen atom, you know the expression will be 13.6 minus 13.6 by n square. Now for 1 and 2, for n value 1 and 2, this energy is perfectly separated. Now if we take the example of 1001 quantum number, then the gap will be very less. Now when we excite with non-monochromatic light like a lamp, so then what will happen, it will simultaneously excite total average area, average electronic state. Okay, so in presence of non-monochromatic light, there's the excitation will be I to F state with a some density of the state, excited state present in the molecule, and incorporating the density of the state, there is something coming out. The rate of absorption will be proportional to the density of the state, and that will give you the very famous and applicable rule of absorption spectroscopy or spectroscopic field, that is Fermi golden rule. Okay, and after that, another thing and the third thing that the lecture covered is the till now these two function shown here is talks about the absorption and simulated emission, but nowhere the spontaneous emission is written. But the thing is that if a molecule cannot be in excited state for a long time, if there is no simulated emission, the molecule eventually goes down to the ground state. So by in spontaneous manner, so there is something known as spontaneous emission, and this is and the idea of spontaneous emission incorporating the stimulated emission and absorption and their relationship of the rate constant is given by Albert Einstein. And you can see that after doing all the mathematics, you can see that spontaneous emission and simulated emission are proportional to the cube of the excitation frequency. So if the gap excitation frequency, or you can see the gap between the two level, so if the gap between the two level is increasing, then the probability or rate of the spontaneous emission will be higher with respect to simulated emission. Okay, so these are the thing, and another thing will be written how this and this is the relationship. So the relationship between simulated emission and spontaneous emission will be is depend on the proportional to the new energy cube of the energy frequency energy gap. Now it also derived the expression of the two rate coefficient A and B, and you can see that the A function is represent the spontaneous decay, is a constant of spontaneous decay, where B is show the transition from state I to state F, and the B and where the only the Z component of the dipole moment is take participate on the excitation. So please look at the lecture, and next week we will discuss about the summarize about the lecture and do the assignment 4. With this I will stop it here. If any question you can ask. I don't think anyone is there, so stopping it.